So today's lesson is about transmission lines, which is, you might ask, okay, what's so special about transmission line? What's so special about them? First of all, what are transmission lines? So you know that we talk about communication methods in this course, and in communication, um, telephone signals, computer data, like internet signal, cable, TV system, they are all gets transmitted and go from like a transmitter to receiver, and sometimes they go through uh, like uh, devices that are called basically transmission lines. Even in PCBs, when you connect like printed circuit boards, which are very small, you connect different like microcontrollers to transistors, you all have these connectors that are called transmission lines. Now, why they are important? Because in reality, when somebody tells you transmission line, like a cable comes to mind or a wire, right? So why it's important that we learn about them, and there is a chapter of the book assigned to it, and there is a course called transmission line actually in some universities. So it's a big subject because they're more than wire or cables. They have their own electrical characteristics, and they must be matched. You will learn about what do I mean by match, but they should be matched to the equipment in order for the successful communication. So they are basically divas. They act differently depending on several characteristics, depending on the wavelength of the wave that is going through it and its length, and depending on its structure. So when you buy even like a coaxial cable, there are characteristics you have to look in the manual to see whatever you're connecting it to is compatible. Okay, so that's the introduction. Now, how would they design them? How would they design transmission lines? When they design them, there are two things in their mind. One is that the attenuation to the signal must be low. So when they're designed, you want minimum attenuation to the signal. So that's one thing. And then you don't want them to, because I'll talk about it more later, but it's like you have current going through a cable, right? So does that mean that it's giving off radiation, radio energy? So the way that it's designed, you don't want radiation, don't want radiation of radio energy. Okay, so that's what they focus on when they want to design transmission lines. And I'm sure all of you have seen like coaxial cables. They're everywhere, even at home. So you know that I'm going to try to draw it. So there are different types of transmission line. One of the most popular one that we have around is coaxial cable. So coaxial cable is just you have an outer plastic insulation, and then you have another like Teflon plastic insulation, and then you have copper here. And they're widely used. You have seen them a lot. Or another example of transmission line can be parallel wire lines, but you don't see them around anymore. Parallel wire lines, or what you see is lots of twisted pairs, right? Twisted pair cables that there are two insulated coppers wires that are basically twisted together. They're using local area networks a lot, so twisted pairs, just some example, coaxial cable, they're all transmission lines, okay? So in order for you to get the concept of transmission lines, I go back a bit, talk about history. Samuel Morse, you know that Morse code, when was it? It was like 1791 to 1872, Samuel Morse. So when he tried to send a signal to a long distance, like a telegraph signal, so he's sending a pulse, and sometimes, depending on this length of the transmission line, let's say my load is here, and you want to get the signal back, what you get is, sometimes you don't get this, you get something like this, right? You get a signal that is not exactly, although you want to get the same signal at the end, you get a copy of it that is basically distorted. Why? Well, because in reality, when you look at a transmission line, you might think, okay, so you have your signal going through. But in reality, as I don't know if you remember from circuit analysis, there is a linear lumped element circuit theory. This theory tells that any device can be modeled as a combination of a capacitor, inductor, resistor, and a source. So in reality, a wire can be modeled as a combination of different passive components that you have learned before. And then depending on the frequency of the signal that go through, you know that, but again, from circuit analysis, you know that the inductor acts differently to DC and AC, and it acts differently depending on the frequency, right? You know that. You know that the capacitor acts differently when you have different frequencies, AC, DC, not resistor, it doesn't matter, and then a voltage DC source. So because of these two elements that are, so the wire is the combination of all these elements. And because of that, this transmission line is kind of, a chapter is assigned to it, or a course is sometimes assigned to it. Because of all these characteristics that are inside this transmission line, it will act differently depending on the frequency and wavelength of the signal you're sending. So that's the idea, okay? So in reality, when you have a transmission line, you can model it as a series of inductors and capacitors. So instead of this, you should look at it like this, because a wire has all these characteristics inside. Okay, so that's why. So I'm going through the behavior of the transmission line. That's why I'm going through all of that and talk about frequency from now on. Okay. So why frequency? First of all, what is wavelength? What is frequency? Let's talk about frequency a bit. So now you have an idea of what's going on. Now, just a refresher about frequency and wavelength. If you, again, remember from physics course, or you don't remember, there is a relation between frequency and wavelength of a signal. Okay, so this is the symbol for wavelength. And what is a wavelength? It's just when you have a cycle of a signal from this point to this point to the end, it's one wavelength. And the unit is, it can be meter. It's the SI unit is meter, and then you can convert it to other distance units. Okay, so that's the wavelength, that's F, and the relation between F and lambda in general is C, which is the speed of light, over lambda. These are all how they are related. And then, well, when you have a signal going through a transmission line, the signal doesn't have the speed of light anymore because of all those dielectrics that are inside. Like, for example, for coaxial cable, you have Teflon, so that would make the speed of signal, that would decrease it, right? So if I want to talk about the general form of F, instead of writing that, you can say F is equal to the velocity of the signal inside the transmission line over lambda. So instead of C, I write V. V is the velocity of propagation. Okay, and the speed in a cable can be anywhere from 0.5 to 0.95 of speed of light. So in in EM, everything scales with frequency. Okay, so if I, for example, if I say I have two, so going back to the example I started, the Morse code, I have a switch here and switch here, and I said I have two transmission lines here and here, right? Okay. And then I said this transmission line can be modeled by a series of inductors and capacitors that are like this. So this is what we learned so far, okay? Now, the question engineers, they ask usually is that, okay, should I be worried when I design a system? Should I be worried about the transmission line, or I can model it as a wire? That's the question I'm going to answer today. Okay. Now, if you look at, I don't go through the maths, but if you model mathematically this system that I just drew here, mathematically, so if this is Z in this direction, if this is Z, so I have voltage going through and current. The equations will look like this. So this is the second derivative of voltage, that the voltage signal going around Z, going through Z, over Z minus LC, the second derivative of voltage, over. So beautiful. You see, you have the voltage signal going through the wire, and you have LC here in your equation. As I said, I don't go through the, I don't go through the maths, but this is what they get when they model a transmission line. So the voltage, the second derivative of voltage minus LC is equal to 0. And the same thing for current, because whenever you have voltage, you have current, right? So same thing for current. Then you have LC. Oops. Okay. So the moral of the story is that by now you should look at you should look at your coaxial cable as a combination of inductors and capacitors. Okay. And then some physicists and mathematicians, they model the voltage and current that go through it. And then if you solve these equations, At the end of the day, you get voltage that goes through Z. Z is the direction, okay? Versus time, they see that they get two voltage signals that are going in both directions. Okay, so when they solve this voltage, these small z's that you see here are the direction. Vp is the propagation velocity. The math doesn't matter. I'm just trying to prove a point here. Okay, so they solve it, and this is the voltage signal that they get inside the transmission line. By V plus, I mean the voltage that the signal that is going this way, basically a traveling wave to the direction positive, and this one is backward propagating wave. So you have wave going into both directions. Okay, so interesting. I have a transmission line. It's a combination of capacitors and inductors are inside. And when I model the voltage signal inside, I have both voltage going forward and backward. Same thing for current. If you write the equation for current, then you will see that you have the current signal going forward and backward. And you know by Ohm's law that V is equal to Ri. Now that I am talking about frequency, instead of resistance, you talk about impedance, right? Impedance is equivalent of resistance when you have AC signal. So I'm going to write the same equation for V divided by impedance, Z0. So then F is my function, again, exactly what I had for voltage, ZP, not VPZ. This is the direction, this is the impedance, okay? I'm writing the same equation I had before, I just divide it by impedance. So same thing for, it's just that here, instead of plus, I have minus. I wouldn't worry about the math. I mean, I didn't prove anything. I just showed you. But the idea is that, okay, so I have a transmission line and I see the equations, and according to the equations, I have two signals going back and forth, and she just talks about impedance. So what is the impedance of this transmission line? The impedance is defined for a transmission line because I have L and C inside. It defines as L divided by C. So inductance divided by capacitance. Okay, so that's the impedance of my transmission line. And the propagation velocity equation is, as I said, the velocity is inside the transmission line. Because of its permittivity, the structure inside, the velocity is less than the speed of light. So I define it as Vp. And I said, and for the transmission line, actually, there is a formula you can plug in, and of course, it depends on L and C. Okay, so this impedance, I'm sure maybe you have heard about it. For example, you say, okay, people see in the manual that the impedance of this coaxial cable, for example, is 50 ohm. That's where it comes from. So that's impedance is because the way it's modeled, or because the way it reacts to transmission of signal, that all these inductance and capacitance come to life. Okay, so far you know that, okay, so this transmission line is modeled by this structure. If you have DC going, if I just don't talk, if I don't think about the transition time, meaning when for example, if I have DC here, like a battery, after I close it, and because when you close the switch for a very short time, you have transition behavior. That means that the inductors will see a change in current and they act, you know, that the inductors don't like change, right? And they backfire. But if I go through that and in a stable state when I have DC current, then this will act just like a wire. Transmission line acts like a wire. Why? Because these capacitors will charge and inductor is just a coil of wire for DC. Again, just a review for inductor. You know that the inductors, when you have DC current going through it, it's just like a coil of wire and nothing will happen. It's just exactly like wire for DC inductor. But when you have change in current, inductors in general, they, because of the magnetic field that it created inside, it will collapse and it impedes the flow of current. In general, the way to remember is that the inductors, they don't like change, okay? So if you don't have any change in DC, it will act like a wire. Otherwise, you should be careful with it. It will create impedance to the flow of signal when you have change in current or voltage. So if you have like DC in a steady state, it will act, the transmission line will act like a wire, okay? So far, you know that, okay, by now, you shouldn't look at the transmission line as a piece of wire. You should look at your coaxial cable as a device that has inductance inside and capacitance. So and it has impedance because of that. And that impedance is a square root of L over C. Okay. So when would you consider a conductor, a current carrying conductor, a transmission line? Because if the signal doesn't change, it will act like a wire, and I don't care about these inductance, right? When you have, so DC means that the frequency is high, the frequency is very low, right? So it's like having a wavelength, like, how would I say it? Like, okay. Now, let's move on to see when I would consider a current carrying conductor a transmission line, and when I just treat it as a wire. So there's a rule of thumb. I'm going to write it because it's very important. So a pair of current carrying conductors is not considered to be a transmission line unless, so this is the important part, unless, remember I talked about frequency and I said everything depends on frequency, unless the length of the conductor is at least 0.1 times wavelength of the signal, wavelength of the signal. So because you have a transmission line and you have a signal going in, right? But if the wavelength is very large compared to the length of your conductor, that wouldn't cause any problem, and these inductors and capacitors wouldn't be bothered, right, for this case compared to this case. So as a rule of thumb, they say as long as the length of your conductor is more than 0.1 lambda, 0.1 is very small, right? 0.1, right? As long as it's bigger than that, the length of your wire, then you have to treat your conductor as a transmission line and worry about its impedance and stuff like that. For example, you're all familiar with like outlets that give off 60 hertz signals, right? So 60 hertz power lines, let's assume that the velocity is the speed of light, because usually it's point something a speed of light, right? The velocity of your signal that's going forward. So inside the transmission line. So that means, if you remember, I said lambda is the speed of your propagation over f. Now, speed of light, you know that it's 3 times 10 power of 8 over 60 hertz. That will give me 5 times 10 power of 6 meter. So you should pay attention to this number. This is a very big number, right? It's several thousands of miles is my wavelength. Okay? So for this case, you don't have to be worried about transmission line. At these low frequencies, the transmission line acts as a carrier of the AC voltage, and you only have resistive loss. Because look at the wavelength. It's so big, right? Now, another example. Now, what if I have this frequency, like 3 megahertz? If I have 3 megahertz, then what would be lambda for speed of light? So it will be 3 times 10 power of 8 meter per second over 3 megahertz. The value you get is 100 meter. So that means your wavelength is 100 meter. 100 meter is like a length of a football field. That's a big wavelength as well. Now, so as I said, the rule of thumb is that the length of the transmission line should be bigger than or equal to 0.1 times that. Okay, so that will give me 10 meter. So this is 100 meter. As long as I have 0.1 times 100, which is 10 meter, then if 10 meter is the length of my transmission line, then this conductor I'm looking at is acting like a transmission line. And all of those baggages of impedance and capacitance and inductance will come with it, okay? So if you have a cable 10 meter and larger, then you have to look at it as a transmission line. Another example, let's say my frequency is 450 hertz, megahertz. This is another frequency. Now lambda is, if you do that, you'll get, this is actually the example of the book for this frequency. Your lambda would be 2.19 feet. So that means 1.1 times lambda is 0.2 feet, okay? So if I get, for example, the transmission line, I want to design a transmission line that is 3/8 times lambda, then that means it's 0.375 lambda. This transmission line with this length, and lambda was what? It was 2.19 feet. It gives you a number, and that would be the physical length of your transmission line. This 3/8 is just in the book. It says if I have a transmission line with the length of 3/8 times lambda, which would be transmission line because it's bigger than 0.1, right? What is the length of the transmission line? So what you have to do is calculate your lambda by doing C/F. Once you calculate your lambda, you multiply to 0.3, you get the length of your transmission line, which is, the number is 9.84 inches. Okay, so far what you should know is that when you have a transmission line like a coaxial cable and so on, twisted pairs, any kind of conductors that you have, if the length of this should be 0.1 times lambda or bigger, so that you treat it as a transmission line. And with that, that means you should look at this as this. So that's what we said so far. And the other thing I said was that when you look at the equations that define the transmission line, you would see that you have waves, that I'll get to it later. You have waves, signals that goes this way and this way, both ways. You have waves that are going forward and then it reflects back, basically. Okay, so having that in mind, let's talk about, I already talked about velocity of the propagation of your signal going in. Why I talk about these transmission lines? Because when I move forward and I talk about antennas, antennas are just conductors as well, right? And you will see, if you understand this, then it will make your life easier when we cover antennas. So when you have a transmission line, you have impedance, right? It has an impedance. Then there is a generator here, and you usually have a load and then another transmission line that your signal comes back, right? Then you have, for example, AC. Now, another thing you should know and keep in mind is that, okay, so this transmission line has an impedance and my load has an impedance. and my generator has an impedance. As long as all these impedances are matched, everything is good. But once, for example, if the impedance of this transmission line is not matched with the load or whatever that is here, that is when the reflected part will occur. Okay, so it's the same thing as resistance. Resistance like impedes the flow. Here you have a wave. According to the equations, you have your voltage going this way, right? And then I said, when you look at the equations, there is a reflected part. That reflected part will come to life when there is an impedance mismatch between components. So, for example, if this is Z prime, this is Z, you have reflection of your signal. Your signal will reflect back. But so that's called impedance mismatch. But if they are all the same and the impedances are matched, that's actually good because I'm not wasting any power. That's why when you buy a coaxial cable and you look at the impedance, it's important that it matches with, for example, your receiver. Otherwise, you have reflected wave, and that will reduce the power. So the best scenario would be this when all the impedances are matched. If I have it, if I wrote it here. So we'll talk about impedance mismatching and matching later more, but for now, keep in mind that, yeah, I can't find it now. Yeah, we'll get there. Yeah, but for now, just remember that when you have matching impedances, that's where you have maximum power. And so you're using all your power because nothing is reflected back, right? So this is the criteria for maximum power transfer. If you want maximum power transfer, you have to match all your impedances. How do you get the impedance? Like the cable manufacturers always specify impedance on the manual. So, and how they get it, it's just the equation, as I said, is L over C. Usually for coaxial cables, what you see is 52 ohms or larger. So that's where it comes from. And as I said, this impedance only matters if your length is larger than 0.1 wavelength of the signal that comes in. So you have to keep in mind all of that, okay? Now, if you remember when I was talking about the velocity of the propagation wave that goes through the transmission line, I said I started by considering the velocity of light. If you remember, I said the frequency is c over lambda. Then I corrected myself. I said, actually, this is in cable, so you have a propagation velocity that is happening inside over lambda. So this is the correct form. Knowing that, first of all, what is this VP? I think I wrote the equation. The VP, or propagation velocity for the signal going through the transmission line, is 1 over LC, the square root of LC. So again, I'm going to say it again. The important thing is that the transmission line, the speed of the signal is slower than the speed of light, or the speed of signal in free space, which is equal to the speed of light. So knowing that, there's another term that is called velocity factor that is defined by Vp, which is the propagation that is smaller than Vc. So Vp over Vc is called velocity factor. Okay. This is called velocity factor, and Vc, a speed of light, as you know, is a constant. 3 times 10 power of 8 meter per second is the speed of light, which is constant. And then whatever propagation velocity you have over that is the velocity factor. And as I said, Vf is usually 0.5 to 0.9 times Vc is usually Vp. So velocity factors in transmission line vary from 0.5 to 0.9. 0.9. That's the Vf usually for transmission lines. Okay. Now, so by now you have like a general idea about transmission lines. You know how to treat them. You know that the length matters, how wide matters, because it has to be bigger than 1.1 times lambda to be considered as transmission line. So so if somebody asks you what is the length of the transmission line when Vf is 0.6 and F, the frequency of the signal that goes through, is 30 megahertz. So they say I want to, okay, so let's just start. What's the length? So I know that lambda is Vp, propagation over F, right? So I know that lambda is always did I write it? Did I do it backward or no, it's correct. Okay, so F is 30 megahertz. What about Vp? So you know that Vf, I defined it as what? If you, Vf is Vp over Vc, the propagation velocity over speed of light. So Vf is given Vp over Vc. Here is Vp. So it's this times 3 times the speed of light. So that will be 6.5 times Vc. And then lambda will be, if you do the calculation, would be 21 times 32 feet. Okay, so that's lambda. Now, I want my transmission, because I want a transmission line, let's say the length is, so it should be bigger than 0.1. So let's choose 0.25 times lambda, which is 21, 32 feet, will be 5.33 feet, will be the length of the transmission line, that is the quarter of the wavelength. I think the question, this is one of the examples of the book. It says, what's the transmission line length if it is the quarter of the wavelength? So you start by getting your wavelength, which is Vp over F. What is Vp? You know, it's propagation velocity, and it depends on Vf in this manner. You calculate it, and then that's what you get. Okay. So, okay, so now you have a general idea about transmission line and all of that. Now, you might have different scenarios for the load here. So sometimes you have a generator and you have transmission line. Sometimes you have a load that its impedance is not matched with the impedance of here. Sometimes you have short circuit here. Sometimes you have open circuit here. And in all these scenarios, there is an impedance mismatch, right? So you have the wave that's going forward and coming back. This situation is called a standing wave. And on Tuesday, I'll go over them one by one now that you have a general idea of what's going on. Why this is important, I just want to give you some motivation for the next lesson, because when I talk about antennas, I have a transmitter that sends information, right? And then I have a receiver that gets the information with my antenna. And then I talk about, for example, dipole antenna, which I talked about a little bit, I think, in the beginning. And it looks something like this. And then I say that because, if you remember, I said that you have carriers traveling back and forth, and because of that, you have electromagnetic wave that is emitted from these wires. But then the question comes, what are you talking about? This wire is up in the air, and you tell me that the carriers are going back and forth? How can it be? Because what you're used to is that you have to have like a closed circuit for carriers, right? That's what you're used to. And then when you look at the antenna, you see it loose in the air. And then you know the theory that you have radiation because the carriers are going back and forth. And it doesn't make sense because it has to be a closed circuit for my carriers to move. Otherwise, how can it be? And it's all because of this transmission line that I just told you, and because of the standing waves, and because of the impedance mismatch. And that's why you have the waves going forward and the waves going backward. So if I'm careful with the wave, with the length of here, which is usually lambda over 4, then I have a standing waves, which result into transmission of electromagnetic waves because of the standing waves that is created inside. So whatever you're learning is all connected and will make sense when you look at the antenna. Otherwise, if you don't know about transmission lines, if you don't know about these standing waves going back and forth, and if your only background is, I have a wire, I have resistance, my wire has resistance, and it becomes heat when the current goes through it, right? This is all I know. I look at it as a wire. This is what you have seen so far, right? Now I guess you can see more. You can see a wire and not only see a wire and resistance, but see inductors and capacitance inside. That's what you have to see now. And that's why, because of that, if there's a mismatch in impedance, you have standing waves, you have signal going back and forth, and then this antenna would make sense. Okay? Any questions?